Welcome to Odor Always Moves, the video series that translates the complexity of odor movement down to the operational level for canine trainers and handlers. This is the second video in this series, and we're going to be talking about Bernoulli's principle, specifically the effects of wind velocity and pressure differentials, as well as eddies. As before, these videos are all dedicated to my first bomb dog, Daisy. And typical disclaimer, hey, this is for educational purposes only. It's not meant to show actual extensive odor or specific odor properties. This is just to show people how odor moves and concentrates in a general concept. So if you want higher level analysis, feel free to reach out to me or others. Otherwise, this is just to educate you on the topic of fluid mechanics in relation to odor movement. Now, just to recap our last lesson, odor availability is directly tied to vapor pressure and available surface area, and it can vary greatly between source material types, and I showed that it was as much as 10 orders of magnitude difference. And advection is the primary mover of odorous gases. And this can be from a natural or artificial source of movement, such as wind or fans or ventilation systems. But the bottom line is, if the air is moving, the odor is moving with it. And to remember that air is a fluid, so it flows around and over obstacles, and the odor will go with it around and over those obstacles. So understanding that and how those obstacles affect it can help you visualize odor movement in the environment you're working in. Bernoulli's principle is one of the key things in fluid dynamics, and it's a lot more complicated than what I'm going to go into here. So if you're an expert on fluid mechanics, don't freak out. We're just doing the real simplified version here. The key things I want from a canine perspective is in a steady flow, like a streamlined flow, so no turbulence or anything like that. The speed and the pressure of the fluid are tied together. The faster the fluid, or air in our context, faster that moves, the lower the pressure is. And conversely, the slower the fluid, the higher the pressure. This is essentially how the wing of an aircraft creates lift. The air flow going over the top of the wing is faster and has a lower pressure than the airflow along the bottom, which has a higher pressure. Now, the reason that works for an aircraft wing is that in a system, the pressure wants to be equal. Okay, meaning that if there's areas of high pressure, it will always want to flow to an area of low pressure, taking that path of least resistance. And in our context, in the canine world, it doesn't take a lot of pressure difference to cause that air movement from a high to low pressure zone. Now, the pressure differentials that do occur, they can have a pretty dramatic influence on the odor movement, but they can be created by a variety of things, including wind speed, which we kind of talked about. The faster the speed, the lower the pressure, but also temperature is really one of the big ones. Higher temperatures create increased pressure, and the reason being is that the molecules get excited, the molecules of the gas in the air, and the more heat you put into them, the faster they move. The faster they move, they want to spread out, and that creates an increase in pressure. And then conversely, the colder the temps, then that decreases the pressure because the molecules are slowing down. But another factor on pressure differentials can be mechanical. The sudden opening or closing of a door can change the pressure and thus the airflow. So how the heck does this apply to canine work? Well, as we said, that fast airflow creates a low pressure zone. And that flow, that kind of air column, if you want to call it that, will pull in the surrounding air into it because it's lower speed or not moving at all, and it has a higher pressure than that faster flow, along that streamlined path. Now, this is applicable if you have that flow going along the edge of something, along the side of a building or a car, because what's going to happen is that fast flow along that outside edge is going to create that low pressure zone, and any openings to that interior area will allow a path of that higher pressure air to flow out. And remember, if the air is moving, the odor is moving with it. So if that high stream flow is going along the side of a building or a car, it can be pulling out that interior air and thus the odor out those openings. So let's take a look at it from a context of real world situation. Imagine we have a trailer house here and somebody's inside of it and they're going to be emitting an odorous gas. And what we're going to do is we're going to have a model that's going to start at 5 miles per hour from the left-hand side, and it's going to work along that flow. And it'll then increase as the model goes up to 10 miles per hour. And you'll notice that there's one open window just downwind in the next room from the person, but the window in the room that the person is in has a small crack in it. And also, all the doors to the bedrooms and other rooms all have gaps in them, like a real door does. So before we run the model, let's take a look at the velocity and how the airflow is going around that trailer house. It's coming from the left side, and this is the colors you see are showing the peak velocities at 10 miles per hour, and you can see the airflow as it hits this upwind side. You have a low velocity here, and that's where the air is basically having to force around that side, and you have a very low velocity area here on both sides of this. But then that flow gets more streamlined and follows the sides of the camper or the trailer house, okay? And that's what we're going to be most concerned about. So here's where that window is that has the crack in it. This is where the person is inside. You have another window downwind that's also open. But you also notice on that downwind portion, there's almost no wind velocities. And that's where eddies are going to occur. And we're going to talk about that in a little bit. But that this is a critical thing to understand is how the flow hits outside and then works up and around, but gets back down into kind of streamline right along the side of that building. Now, before we do the full animation, let's look at what that airflow is doing in relation to pressure. And what it is that upwind side where that wind is hitting that flat air end of the trailer, that's a high pressure area. So odor is not likely going to be coming out of there because the air pressure is too high relative to the interior of the trailer house. But along the tops and the sides, where that airflow is nice and streamlined and fast going along the face of it, those are creating low pressure zones. And then you also have a low pressure zone on the downwind end. And again, that's going to be partially due to the eddies that are going to be created there. And just the fact that there's no wind pushing against it, but all the wind is going past it. And again, that wind, that surrounding air wants to go to that faster airflow because it has that lower pressure. So let's take a look at this with the animation. So the airflow is coming from the left, starting at 5 miles per hour, and that person is breathing, and they're emitting their odor, and you start to see it maybe try to come out that window, but the room's still filling up and hasn't reached equilibrium yet, and it won't just because it's not a closed system. But now you start seeing odor get pulled out through that window gap as the wind is flowing along it. And you see a little bit actually going out into the hallway too. But then now you're starting to see the velocity start to increase from that 5 miles per hour up to the 10 mile per hour area. And as that wind picks up and that pressure on the exterior of the trailer house decreases, more and more of a suction effect occurs. Because again, the pressure inside the trailer house is higher than the outside because of the wind speed running along the edge of it. And so you can see that odor being pulled out that window gap downwind and maintaining a decent concentration as it goes. So, and you can see the rest of the trailer house, it's filling up with odor, spreading out as it normally would. But you also see the areas inside, downwind of that room. There's more turbulence in that area because there's that open window just downwind of that room. And so you see some movement in there. So that's a good example of the Bernoulli principle in terms of the wind speed along the outside, nice steady state flow. and having a lower pressure, and that lower pressure pulling that odor out of it. Now we're getting to where the topic of eddies, and an eddy is just where a flow circulates on the downwind side of an obstacle, and is proportional to the size of the obstacle and the wind speed. You know, what's important to understand is that the motion of that airflow in the eddy and the lower pressure it creates relative to the surrounding area will result in that surrounding air and odor being pulled into them. And it is important to understand that eddies can occur either vertically or horizontally. So you can kind of see the directional areas of a flow over a trailer house, and you can kind of see going over, vertically hitting on that backside like the animation in the prior slide showed. But then looking down from the top view, you can see that it's creating two different eddies on the backside, starting at one end, but then circulating back to the center and then circulating back around. And so that backside can be a very complex area in terms of air movement. Now, another thing to remember with eddies is that they're not stable, okay? But they'll actually quickly collapse and then reestablish. And this kind of creates a pulsing effect in the air movement behind that object. And this is kind of showing that you have the directional arrows and then the magnitude, the velocity magnitude as it, the vortice or the eddy, the eddy will establish and then kind of collapse, establish, kind of collapse. And it just creates this unstable area behind that object. And that can influence how odor builds concentration and maintains it for detectability. It doesn't make it impossible. It's just something that you have to remember when you're working on a downwind side of an object. So if we look at that same trailer house and look at the flows going over it this time, instead of looking at it from the top view, you can kind of see that same effect where the eddy establishes and kind of pulses and, kind of collapses, kind of reestablishes. But the other thing is it's going both up the backside of the camper or the trailer, but then also kind of down to the ground. And so depending on where your dog is at and searching high and low, that's something to kind of remember is when you're working on those downwind sides. Again, just the complexity that eddies cause in relation to air movement and thus odor movement. So what does this look like, in like a real world setting in relation to odor? So we're going to use a search and rescue scenario. This is a collapsed structure. Buildings collapsed, however, earthquake, whatever. And you can see some partial walls still standing, one on the left, one on the backside. And you can see all the rubble and debris. But what you can't see here is that buried beneath that is a human being. And they're breathing. And that's what I use for my odor source, so about 6 liters per minute. And I just use the properties of what a person exhales on any given day. Okay. Now, what does that look like with no wind? Okay, so this is after 20 minutes. And it slowly worked its way out. That's the extent of the odor. Now, remember from the last lesson, the color ranges. These are always going to be 2 orders of magnitude concentration levels. So you can see some red within the rubble itself because it's made it transparent so you can see. But that red is 100 times more concentrated than the blue limits that you're seeing. Okay, so that's after 20 minutes with no wind. Now what happens if we do a 5 mile per hour wind, so 2.2 meters per second? So let's take a look at that. And you can see the odor is pulling out against the wind. And then it's caught up on the backside of that wall and it's pulled down. So what you're seeing is that eddy effect. So that eddy was created by the wall, pulling it back, creating an area, a pocket, where the odor stays for quite a while. It concentrates decently. But notice the odor plume downwind as it gets caught up into the main flow. You can see the odor plume try to go down and it tries to establish a stable form of concentration, but it can't. And we'll get to that why in a little bit. But I want you to see how it tries to reach out, tries to stay concentrated, but then it breaks up. Tries to stay concentrated, breaks up. And that's going to be an issue. If you're running a dog at that downwind portion, the dog's going to be in odor, out of odor, in odor, out of odor. And what's occurring here is the effects of the wind speed and how it influences areas of concentration on that flow. Now let's take a look at the wind velocity in relative to that model we just showed. This is just going to be a cross section. And we start the animation, you'll see the wind speeds. Again, the reds and the yellows are faster velocities. Blues and the greens are the slower velocities. But we'll kind of see that vortice or that eddy effect on that downwind side. Okay. And what's important to remember is that that motion of the eddy is pulling that odor in. So it's really advection. The faster wind going up over the wall is a low velocity. It pulls the air on the backside of that wall up into that flow, creating this circular motion. And that air going up the backside of the wall is pulling the air along the ground and just creating that circular motion. And it's pulling that all the air in that rubble pile into it, including the odor. Now, this may be a little overwhelming at first, but this is probably one of the most illustrated images that I have for this whole thing. And so take a second to orient yourself. The lines that you're seeing are called streamers, and they're really just particle pathways of the airflow. And the colors are based on the velocity. So again, the reds are faster, and the blues and the greens are slower. And this is just a snapshot, but you can see the odor being pulled out initially from the pile towards that wall, and you can see the swirling effect caused by the eddy. Okay, and again, that's the result of that high velocity arching over that barrier, and creating that low pressure flow, and then pulling the air on the backside of the wall up and creating that circular motion. And what you should look at is those nice straight lines, or relatively straight lines along the bottom that are red, and that's a laminar flow. So basically that's an area of flow with not any turbulence in it. And that's what the air wants to do. In a fluid, it wants those nice laminar flows, and it always try to get to a point where it's established in that. Now, if you remember, the odor plume would try to work downwind, from that wall, but it would never be able to maintain concentration. It kept breaking up, kept it'd make it a little bit, then it would disappear, make it a little bit and disappear. And you can see in kind of midway up the model, you can see some swirling effect right above those red laminar flow lines. And what you're seeing is a lower velocity flow mixed in with turbulence caused by the rubble, intersecting with that undisturbed high velocity laminar flow. And you're creating a thing called shear dispersion, and that's where you have flows of different velocities intersecting. And it basically just shears the odor apart. And the main effect of this, and this is important from a canine standpoint, is when that occurs, the concentration of the odor will diminish and be less detectable. Okay, so anytime you have low velocity flows interacting with higher velocity flows, and then just combining that with just the turbulence from obstacles and such, it just reduces the concentration. And we covered that in the advection portion in the last video. So let's summarize things. The speed and pressure of a fluid are tied together. Okay, the faster the fluid, the air in our context, the faster it moves, the lower the pressure, and conversely, the slower the fluid and higher pressure. This is in steady state streamlined flows. Okay, doesn't as soon as you throw turbulence in there, that all changes. Pressure, which wants to be equal throughout a system, that's a key, because high pressure areas will always flow to a low pressure area, taking that path of least resistance. So, we use the example of a streamline on the outside of a building or a car, and that fast flow on the exterior creates a low pressure, higher pressure inside the vehicle. The air inside will want to find a path out to it, taking the odor with it. And then eddies form when air moves around or over an obstacle. And the faster the air flow and the more significant the obstacle, the larger and stronger the eddy is going to be. And that lower pressure and the air movement of that eddy will tend to pull odor into it. So upcoming videos, next one's gonna be on just air flows and eddies, kind of continuing that thing. Specifically, we're gonna look at how the external air flows around a building can influence the internal movement of air. And then just upcoming topics, no particular order. We're going to look at ventilation systems inside structures, mountainous terrain for search and rescue. We are going to eventually get to that search and rescue open water and then triangulation center mass methods for locating a source. And urban terrain, the Venturi effect, and lots of different things, and buried hides and much more as time permits. So that's what's coming down the pipe. I thank you for your time. If you have inquiries or questions or would like more specific models for maybe your facility or agency or even in-person teaching, please reach out to me at this email address. And if you want to follow the antics of my dogs, I currently only have one, Dante. Our Instagram is Rotten Bomb Dogs, and feel free to give us a follow. Thank you for your time. Hope you have a great rest of the day.